All right, good afternoon. Let's start lecture. Okay, so let's continue our lecture. Judging from the tendency, I have two guesses. Either you have a midterm coming or you have a holidays coming. Okay. Good. So, there's no holiday coming, right? Yeah. Let's continue on the directional derivative. Yeah. What's probably next week now. Yeah. A lot of paper to mark. Want to help out? Anyway. Okay, in the previous lecture, we talked about the directional derivative. So let's just quick review it here. So if you have a function given, then if you're asked to do a directional derivative calculation, and this is the notation for directional derivative, then the formula is basically equal to the gradient of the function dot the direction of the change. Okay, so the direction of the change is given by u hat here. Okay, so basically make sure that this is a dd. Okay, so I'll call this directional derivative as a dd here. Okay, and this is a gradient, and this one here is a direction of change. So you go along that direction u hat by a small change, then the rate of change in the function f will be given by this dot product here. Okay. So now let's finish one loose end here. Let's finish this directional derivative. Basically, it's a concept of estimate changes. Okay. Now this is not a new concept. Okay, it's not a new concept. So, but we wanted to provide a more general solution for estimating changes when there is a change in something else. So I'm gonna before we summarize that, so let's just remember the quick review on a small one here. If you wanted to estimate a change, okay, for a function single variable, all right, this is single variable here. So now what do we do? And basically, if you have a function here, you take this derivative, you have a df over dx, okay? Then, for example, maybe it's equal to, okay, without giving the function. So that's your derivative at here. So if we wanted to estimate the change, what we do is, this is estimation change delta instead of straight d. This is delta here, right? It's approximately equal to its derivative times delta x. Right? Yeah. So that's for function of single variable how you can estimate change. If there's a change in x direction, positive x direction, then how much a change in this function at here. So right. So if this delta x is 0.1, and then you can calculate this one here at a certain point, then you can calculate this delta f equal to something. Okay. That's a simple case for function single variable. Now if you deal with function of two variables. Okay, so let's say we have function two variables here. And this one here, we actually solved this already. Okay, so in this case here, then estimated change, the proper formulation of the problem will be, okay, initially you are at a P0 location, and now goes to the final location, which is, let's say, call it P1, and that you basically give a small change to the x and y component. Okay. So that's for function of two variables here, right? Yeah. So if you change from this point to this point, then the question here basically is how much change in this function f at here. Right? That's estimating change. Okay. Yeah. So in this case, if you recall that this is actually basically one of the midterm question. Okay. Then what we do is we basically borrow the total differential formula, right? So total differential formula, if you remember, it's a df over equal to fx dx plus fy dy. So what we do is we basically change the straight d to delta, and then right, and then do the calculation. So that's estimating change for a function of two variables, right? So more precisely, if I write this one using a little more information, because we're talking about estimating the change from this location to this location at here. So this is basically fx at P0 location plus this fy at the P0 location delta y. Okay. So that's what you do for function two variables, right? And this formula right here, okay, you can write it in a dot product format, okay, and that basically is delta f dot vector delta x delta y. Okay, so that could be shortened in a dot product format, right, for this expression. Good? Yeah. So this is the second case. Now if you take another look at the second case at here, so initially at here and then finally end up at here. So if I change the description slightly, right? So I think you starting from P0 location, okay? Starting from P0 location, you go to P1, so it's like this. So P0 at here, then you go to the P1 at here. Okay. So basically, you have a surface z equal to f of x y at here, and then this is P0, this is P1, for example. Right, so that's what happens. You go from P0 to P1, and then what's the change, right? Correspondingly on the surface z there. Okay. So that's another way to look at it. Now, when you see go from P0 to P1, so I can write a P0 P1 vector, and the P0 P1 vector is turned out to be delta x delta y. Okay, yeah. That makes sense? Okay. And second of all, when we see going from, now this is essentially a direction concept, right? This is a direction concept. So go to that point in this direction, and by how much, right? So you go to that point in that direction by how much? So let's call this delta s. So the delta s that are here, and you can calculate, which is the norm of this vector at here, and the delta s is delta x squared plus delta y squared. Okay. So now you see what I'm trying to get is basically try to transition into the third general case. So we're going from one point to another point. Basically, it's the same it could be equivalent to be said to go to certain direction by a certain amount of displacement, right? So that's another way of looking at this question here. So this is essentially the third case, okay, the more general case in terms of the estimating changes here. So generally, okay, we estimate change for, let's say, for example, function of f of x, y, or even more variables. Okay, so we will really stop at 3 variables, but you can absolutely extend to more than 3 variables here. So let's say we estimate change for this function f or one variable here. So in this case here, more generally, is in a direction u hat for a small distance, okay, for small distance delta s. Okay. Yes. How small? Maybe it could be as small as, right, the smallest distance is ds, infinitesimal small, that's ds. Okay, yeah. That's the general case. So for the general case, then what would be the formula for calculating or for estimating the change in the function f then? And the formula comes directly from the directional derivative formula. So directional derivative formula, if you recall here, as we just wrote it down, is df over ds in the u hat direction, for example, at a certain location p naught, equal to the gradient at that location p naught, and times u hat, right? A dot u hat. That's directional derivative formula. So now you can see, if I relate this formula to the general description in here, this is the direction of going. This ds, you can think of it as a small change in that direction, right? So now I can see, basically, for this, based on this formula, I will multiply this ds to the right side of the equation right here. Then I would be able to get a writing for this df now. So delta f at p naught dot u hat, okay, and then times ds, okay, times ds. So this is from here, directly from this directional derivative formula here. So the first portion right here, this is a directional derivative, and this term right here is the distance increment. It's actually in the same format as a function of single variables, right? You know, when you have function single over df over dx is f prime, and then df equal to f prime times dx. Okay, that's the same kind of format here. Okay. Okay. So in terms of estimating the change, this is equal here. So we can change the straight d to delta. So the delta f will equal to so that's the estimating change formula. If you go from p naught to the direction u hat by a small distance delta s, then the estimated change in the function f is given by this particular formula. Okay? Yeah. Okay. So as a matter of fact, we call this as a general case. Basically, this particular case should include all the case 1 and the case 2. Okay, that's why it is called general case, right? And I can show you basically how this is actually, this one here include the case number 2. So let's say here, right? So let's consider a specific case. If we let, for example, let's see, our u, okay, give a direction of a change. So here's the direction of change. So this is basically the case in the second case, right? So you have a small change from current location, delta x, delta y, but this is not a unit vector, so I'm gonna normalize this vector here to be a unit vector. So basically divided by its length. So you get the unit vector. So we're going to go from initial location to the direction given by the unit vector here. And then by how much distance or how much displacement, and the displacement here, as in the second case, is given by delta x, delta y squared, right? That's the second case. From here, you move this much of a displacement to that direction. Okay, so now I have a direction, I have this displacement, then I'll substitute into this formula given by the general case number 3. Okay. So let's see what do we have. So we have a del f at this location p0 dot u hat, and then time delta s. So that's the formula, right, for the third case. So if I plug it into this formula, plugging all the available vectors, functions into this one here. So what do we get? Basically we get fx times, okay, the first component here, first component, so delta x over its length, and then plus fy at p0 times delta y over this thing here. So that's the dot product. Okay, that's the dot product. And then the whole dot product will time the delta s, so delta s, which is delta x squared plus delta y squared. The whole thing here times delta s. Right? According to this given information. So now if you multiply this term into the bracket, right? If you multiply this term into the bracket, basically you're gonna cancel those terms on the denominator there. Okay. So then this equals to fx p0 at p0 location times delta x plus fy p0 times delta y. Good? Yeah. And this is your delta f, right? This is the delta of f is approximately equal to this. Or delta f is over here. Okay. So now you see this formula here, that's exactly the same as the formula for the second case, right? The second case. So basically, from now on, if there's a question regarding estimating change in the function f by going to a certain direction of a certain amount of displacement, so now all you need to remember is it's just this formula now. Good? It's just this one. Okay. But you all have to understand is what each one of the term and here represent, right? And what's the physical meaning for each one of the term. Okay. Yeah. So let's look at one example, then we'll wrap up. Okay. So let's take a look at one example here. I'll give you a function f of x, y, z, so function 3 variables. So f equal to this, and we wanted to estimate the change in f, okay, the change in this function f, if a point, okay, and it moves from initially 0, 1, 0, okay, straight to another point 2, 2, negative 2 by 0.1 unit. Okay, so that's the question right here. So unfortunately I can't illustrate this because it's a function of 3 variables, so we can't graph this one here, but in your mind you can picture there's a point at the P0 and there's a point at the P1. So you go from P0 to P1. Now you don't go from P0 end up at P1. In this question is you go from P0 to the direction given by the P1, right? And then basically you go along that direction by how much distance? By a 0.1 unit of distance. That's basically the question. And then how much variation, how much change in the function f at here. Okay. So everything is basically it's related to this formula at here. So if you can figure out all the components given by this formula, then you'll be able to figure out this change in the function f at here. Okay, so this is how you can do it. Let's figure out the u hat first. As I said, u hat is not P0, P1. It's the P0, P1 normalized vector. Okay, so if you normalize this vector, then you will get the u hat. So we can calculate this vector P0, P1. Use the P0 vector minus P1 coordinates. So that's 2, 1, negative 2. 2, 1, negative 2. And then its length is the 2 squared plus 2 squared plus 1, so 4 plus 4 plus 1, which is 9. Then square root is 3, so that gives you a 3 at the bottom here. So your u hat is 1 over 3, so 2, 1, negative 2. U hat. So we've got a u hat. And what else we need? We need the greeting vector at here at the P0 location, and we also need a delta S. The delta S is changed its symbol. The 0.1 unit is basically delta S. So let's calculate del F at the P0 location. First, calculate the greeting vector. So this is your function f at here. Greeting vector, you have a basically you have fx, fy, and then fz, right? Okay, so given the current function fx, that will be y times cosine x. Fy, so there are a few y here. So fy, that will be sine x, and then plus 2z. Fz, only the last term has a z, so that's 2y at the P0 location. Good. Now P0 is 0, 1, 0, so x is 0, y is 1, and the z is a 0. So plugging into the del f gradient vector, 0 at here, y is 0, so the first term is basically y is 1, right? So y is 1, and this is cosine x. So cosine 0 is 1, so first term is 1. Okay. And then here is sine x, sine 0 is 0, 2, 0, 0, so the second term is 0. Last term 2y, so 2 times 1, which is 2k hat. So that's your greeting vector at the P0 location. So finally, you can calculate the whole thing. You can put the whole thing together. So delta f is approximately the greeting vector at the P0 location dot u hat, then times delta s. Right. So you have a vector 1, 2 at here, dot u hat. U hat vector is 1/3, 1/3, 2, 1, -2. Finally times the 0.1 unit of change. Okay, that's everything involved at here. Okay, so you do the calculation here. So it's going to end up with -2/3 times 0.1, which is approximately -0.067 unit. Okay. So if you go that much displacement in that direction, then you end up with a small change in the function f by 0.067 unit. Okay. Okay, so that's basically everything about the directional derivative. Okay, yeah. And we'll come back to this a little bit, maybe not today, or maybe today, or maybe next Monday for sure. Essentially, when we look at the mean and max value for constrained problems. Okay. Yeah. Okay, any questions so far? So good? Okay, so let's move on to a new topic now. Okay, so now we're kind of, as you've all observed, we're jumping back and forth between the vectors and the multivariable functions. So this is, I call this is all vectors that are here. So now we're going to slightly transition back to functions again. Okay, yeah. The topic here is basically it's about the mean and the max for a surface. We can also say we're going to look at extreme values and also look at the so-called saddle points, okay, for surfaces. Okay. So this is an extension to basically the mean and max for function of single variables. Okay, yeah. So what do we mean by extreme value or saddle point? We'll come to the saddle point shortly here, okay? But let's talk about maybe just say the extreme values for a surface. That is quite straightforward here. So let's say if you have a surface, if you have a surface, let's say this is some sort of a change of terrain here. And apparently, when you walk around this surface in the mountain here, inevitably you will see this is not a basically a very good drawing, but okay. So okay, as you're going along, basically what you end up with here. Okay, so you have this is your first peak. And that's a trough here, and there's another peak, and there's another one here. Okay, right? So there's up and downs, but every while you're going to experience some sort of extreme values here, right? Yeah. So these points that are here, this is basically all what we call here. This is what we call the local, okay, local mean or local max, okay, point. Okay, so this red here is the local mean, local max. So for example, this is a local maximum, this is the local minimum, another local maximum, another local minimum. Okay. See the wording in here is, I say this is a local, right? So local mean or local max. So what is local? Because so apparently, see, if you compare this one with this one, and this is a bigger maximum than this one here. Okay. Yeah. So naturally, you will see. Okay, so then if you see local, then there's something like what? There's got to be something like a global mean and a global max. Okay, yeah. So the information about the global minimum, global max, that can be generated if you have the information for local minimum, local maximum. Then you can inevitably you'll get the global mean, global max. Okay. And more to this kind of question is, you typically probably not going to just look at the whole universe or the whole Earth, and you're probably only going to look at is what? Probably just only look at a portion of a surface, right? Just a portion. If you only look at the portion of that, then the boundary values, right? The boundary values could be basically a mean or max. So that boundary values here is another thing that you had to be you had to watch out here. Okay, yeah. So that could be a local. Basically, if you look at this whole piece, not everywhere, just this segment here, just this portion, then that could be a local mean. That could be a local maximum. Okay, yeah. So that sort of idea. Good. Yeah. Okay. So now they pose two questions now, right? Two questions. First question: how do we know this is a local minimum, local maximum? Second question, right? Second question would be, let's say the first question. The first question is, how do we know that this is a local extreme? So local extreme basically including both mean or max, right? Yeah. And the second question is, how do we exactly know that this is a minimum and this is a maximum? Does that make sense? Right? Yeah. That's basically the two kind of questions. Actually, the third question will be, what's the minimum value? What's the maximum value if you're able to tell that this is a mean or this is a max, right? Yeah. So now, if you remember, when you learn function of single variables, so what do you do when you're giving function fair single variable? What do you do first step in order to get a minimum maximum? Derivative, huh? Yeah. So you take a derivative and then you set it to 0. So you solve this derivative, you get a certain value for x, right? Yeah. So that value of x will tell you this probably, right? Not necessarily for sure. This is probably going to be a minimum location or maximum location. So basically, when slope is equal to 0, then you're most probably at a minimum or maximum. Why do I say probably? Because there's one possibility, which is what? Yeah.
Just go straight up into infinity.
Asymptotes. No. Remember this kind of curve? You go here and then goes down here, right? See that point? What would you call it? Inflection point, right? Yeah. So that's what I say. If you take derivative at this point is 0, right? But that's not a mean or not a max. It's inflection point. And this is same thing will apply to the function 2 variables. And that's the point. Remember, what do we call it? It's called saddle point, right? Yeah. So this is your function, a single variable. You do a first derivative test to get the possible extreme locations. And then what do you do next? You will do a second derivative test, right? So the second derivative sign at that location will determine whether it's a mean or whether it's a max. Is that right? So if you remember, if this second derivative is greater than 0, if it's greater than 0, what would it be? Is it a mean value or is it a maximum? Do you remember? It's a mean, right? Yeah. And this is actually if you can't remember these things here, and the way I remember is always to try to remember using the Taylor series expansion, and of course you have to remember Taylor's expansion. And plus high order. That's Taylor series expansion, right? Taylor series expansion. If you look at Taylor series expansion here, so if your first derivative at that location is 0, then this term will be gone, right? And then the other term, the second order term, this is the term basically determining the change of this function here. So this is fx basically minus f naught. If this is greater than 0, basically any value change around x naught will end up with a positive change. So if this is positive change, then it must be the curve must be concaving up. Okay, right? If this is a negative value, then every value around x naught will end up with a negative change, right? So negative change. So that's why one is mean, one is maximum. Okay. So I want to borrow the same concept at this first derivative test and second derivative test to function of two variables here. Okay. So we're going to look at a function of two variables here, okay. And we'll look at how do we find the mean value and the minimum and local mean and local max value or local extreme values here. Okay. So let's back off a little bit to the greeting vector. Okay. Now, if you recall that, I keep repeating this. What is the physical meaning for greeting vector? The vector gives a direction, the greatest change for the function f, right? Okay. So then, what happens when this vector equal to 0? Meaning there's no change. So if there is no change, and that's exactly what we're trying to looking for, right? So this is basically the so-called first derivative test for a function of two variables here. You want to get the extreme location first. Maybe it's mean or max, we don't know, but we want to get the location first, right? So what do? This is basically the so-called first derivative test, and this is essentially the first theorem. Okay, I'm going to write down it here. Okay. So this is first derivative test for local extreme point, extreme locations. So what this says basically what you do is you set the greeting vector equal to 0, or we end up with a partial f or partial x. So let's say I'm talking about function two variables here, right? Okay, so I'll just use function two variables to illustrate. Okay, so basically you set this vector to be 0, and this vector to be 0, and that's equivalently to say fx equal to 0 and fy equal to 0. So you have two variables x and y. You have two equations. Then you'll be able to solve for this set of equations that are here. So the solution basically from here. Okay. So solve fx equal to 0 and fy equal to 0. Give us, let's say, a location A and a B, okay, as a solution. For example, there might be multiple solutions, but suppose that this A and B is a solution. So basically what we say here is this point AB, okay, this point AB is possibly a local mean or local max. So that's called first derivative test. Okay, to get the location for the possible mean location and possible max location. Okay. Now sometimes we call this solution, this location here, so we can call this so-called critical point. Okay, we can call this critical point at here. But as I said, the A and B may not necessarily is a local mean and local max. So that that could be possibly at the inflection point. So same thing for function two variables. So we also have a possibility that the A and B may not be the local mean or local max. So A and B could be the so-called saddle point. So now more precisely then basically what is the saddle point, right? It's a saddle point here. So I think we talked about this already in the previous lectures. Basically, saddle points, more proper definition essentially. You can use this if you go away from this location A, B, okay, if you basically walk away from this location A and B slightly, right, slightly, then there are two possibilities. Okay, if both this fx, fy less than this and f of xy greater than this, if both of these are possible, okay, so you have one potential, you go around from this location, so that surface, okay, function f can go up or go down, okay, as two possibilities, okay, both are possible. Then the AB, okay, is a saddle point. Okay. Very strong static noise there. And we also wanted to basically find out this static point. Okay, yeah, that's another thing here. Good. Okay, so here's the first derivative test. First derivative test only give us the possible location for the local mean and local max. It's not going to give us the exact information whether it's a mean or a max. So that's why we need the second theorem to work with the first theorem. The second one here essentially was what we call second derivative test. Okay. Now this one here will be able to, and once we finish this test, then we'll be able to know what exactly it is. Okay. This is a bit of a long theorem, number 2 right here, so I'll just write it down first. Okay. Okay, suppose we already calculated the first derivative test, and we find the A and B, okay, satisfy this first derivative test. Okay, then we're going to look at second derivative test now, and it'll actually be classified into 4 different cases. then number one, this function f, okay, has a local maximum, okay, at this AB location if, okay, if what? If fxx is less than 0 and fxx fyy minus fxy square is greater than 0 at this AB location. That's the first case. So try to associate this with the second derivative test for function single variables. So this is a little bit complicated because there are two conditions you need to check at here. And both of them are second derivative. This is second derivative, this is second derivative, right? Yeah. And if I got time, I'll show you how this can be proved using the Taylor series expansion for function of two variables. Okay? Otherwise, you can actually just simply memorize this formula, this theorem right here. So that gives us a local maximum. Okay, first give a local maximum. If we test it differently, we'll get a local minimum. Then this time, this fx here, this will be greater than 0, and this fxx, this fyy minus fxy square, okay, this term is still greater than 0, okay, at AB. Good. That's the second derivative test, the second case right here. This will tell us a local minimum location for AB if these conditions satisfy. Okay, very close, just a sign difference. See, right? This is the same, but this is a sign difference for fxx. So that's the second case. Now, third case, if we test, okay, then we'll get the information for saddle point. Okay, saddle point. So this one here basically is fx fyy minus fxy square. Okay, this is greater than 0. This will be less than 0 at the AB location. Okay, if this is less than 0, then it will be basically a saddle point. Okay. Yeah. There is a last case at here. Okay. So the last case is, it says, okay, the test is inconclusive if this fx fyy minus fxy square equal to 0 at AB. So you happen to have that term to 0, then you actually can decide on what that point is, what type of point that is. Then basically you're going to have to do a so-called higher order, even the higher order derivative test, a third order derivative test. Okay, yeah. But for us, that should be enough, okay, to cover the different kind of cases using 1, 2, 3. Okay. Yeah. So this will be a formula given to you in the final exam, but you'll have some opportunity to practice, this formula. I'll give you an example later. Okay. Yeah. Now, look at this theorem here, just slightly here. So there's apparently you'll see there's one term showed up quite often, which is this term here. Okay. So this fx fyy, then minus this fxy square. So that term showed up quite a bit, right? Yeah. This term here, this one here, okay, this is basically called so-called Hessian of the function f. Okay, yeah. And as a matter of fact, sometimes you can write. See, this term here is basically if you put it into a matrix format. Okay. And this is a matrix right here. So the matrix has diagonal fx, this fyy. Diagonal has fx, fyy. The off diagonal has fxy, fyx. And you put it into this 2 by 2 matrix because this is a function 2 variable, so you can form this 2 by 2 matrix. So this matrix essentially is the so-called Hessian matrix. It's basically Hessian matrix. So this matrix, if you calculate the determinant, if you calculate the determinant, and you get that fx fyy minus fxy squared. So this one here, this is called the Hessian. This is called the Hessian matrix. Okay. So that really you don't have to remember this one here, but this is actually a quite important matrix. In mathematics, there are two important matrices. One is called Jacobian matrix, and the other is called the Hessian matrix. So Jacobian matrix is the first derivative, involving first partial derivative, and the Hessian matrix involves the second partial derivative, which is what I show it here. Okay, yeah. And the other thing, the other way to understand this one here, you look at local minimum, local maximum. What really determines the local minimum, local maximum? It's the sign of this fx here, right? The sign. So if you have fx less than 0, it's local minimum, local maximum. If you have a sign for fx is greater than 0, then it's a local minimum. Okay, yeah. So how do you basically interpret this thing here, right? So let's say if this is a less than 0 here, so it's supposed to be a local maximum. So now you can think that basically what it basically saying is you have a surface. If you need that point to be a local, what is it again? Local less than 0. Local. If you need that to be a local maximum, then basically that curve needs to be what? Right, arc down, right? Arc down here. So this sign at here. Okay, so this sign, this fx value at AB, the sign, so determines how that curve will go, whether it's going to go concaving up or going to be concaving down. Does that make sense? Yeah. And that's actually equivalent to the second derivative. When you have a second derivative, it's the fx double prime greater than 0, less than 0, that determines how the curve is going, curving up or curving down, basically. Okay, yeah. So that more or less sort of an interpretation for this function here. Now, for more rigorous proof for the theorem 2, I do have a proof actually about 6 pages. It's actually not that rigorous. I would call it more illustrative type of proof. So if I can upload this one here, and if you're interested, we can sit down and go over this one here. Not a problem. Okay? Yeah. Okay. Let's see. This is done. This is up. Okay. Okay. So let's take a look example here, okay? And I think the more important is to make use of this theorem 2, okay? Proper usage of theorem 2 at here. Any questions so far? Okay. Yeah. So let's say I give you a function, two variables. (8x squared plus 8x cubed actually). 8x cubed plus y cubed plus 6sy. Find all local mean, max, or possibly saddle points. Okay, on all of these possibilities, we don't know, right? So at this stage, it's just all possible. So then you have to basically go through the process to find out the exact information. Okay. So follow the steps here very closely. Okay. Step 1 is the first derivative test. Now what I do is basically you calculate fx, so partial derivative regarding x. So 24x cubed squared plus 6y. Then you set it to 0. Calculate partial derivative with respect to y. And now 3y squared plus 6x, set equal to 0. Okay. Then altogether, you can solve for x and y here. Okay, solve for x and y. Now here, it's not like first year linear algebra. You always have a basically a set of linear equations. Now because the surface can be any type of surface, when you do the first derivative test, and you will probably end up with a set of equations actually that are nonlinear, most probably. Okay? Yeah. Then the solution, the solving for these things here, there is no a very set rule in terms of how you solve a set of nonlinear equation. Substitution is always something that you can resort to. So let's say here, from first one, I can get y equal to negative 4x squared. Then we'll substitute this y equal to negative 4x squared into the second equation in here. Then the second equation basically becomes 3 times negative 4x squared plus 6x equal to 0. Simplify this a little bit. Negative 12x squared plus 6x equal to 0. And 6 can be cancelled. So negative 2x squared plus x equal to 0. Huh? Y squared. Oh, sorry, y squared. Yeah. I missed a square here. Yeah, then I missed quite a bit. This is going to be 3 times 1648, right? This will be to the power 4. So cancel the 6. This is sorry, here. Am I right? Yeah. Yeah, this is 8, right? Yeah. Positive? Oh yeah, positive, that's right. So 8 times x to the power 4 plus x equal to 0. Good. Okay, so a little bit further simplification. Take out the common factor x. Okay, so then you get this. So now you can set each one of the factor to be 0. So that basically give us x equal to 0 is a solution. The other one, 8x cubed plus 1 equal to 0. So that'll give us a solution what? Negative 1/2. Okay, yeah. So 8x cubed equal to negative 1. So x squared equal to negative 1/8. And then you take the the square, not the square root, the cubic root, and you get x equal to -1/2. So there are two solutions here, right? So two solutions for the x. So two solutions for the x, then there got to be two solutions for the y. So you can separate for x equal to 0, substitute into this relationship at here, you get y equal to 0. And then for x equal to -1/2, substitute this -1/2 into the equation at here. So that happened to be 4 times 1/4 and then negative. So that's just basically -1. Okay, so basically the solution at here are locations, are coordinates. We got how many coordinates? We got two coordinates. One is 0, 0, and the other is -1, -1/2, and -1. Okay, so that's two locations, two possible locations for the so-called critical points. And what type of critical points? That's what the second derivative test will tell us. So that's first derivative test. And then step 2, second derivative test. So second derivative test, because we got two different locations, so we need to test each one of them separately, right? Yeah. I guess, but irrespective of what you're going to test, if you look at the second theorem, we need to calculate a number of terms. So we need to calculate fxx, fyy, and fxy, right? So let's calculate each one of them. So fxx equal to what? Fyy equal to what? And then fxy and equal to, what is that equal to, right? It's a very simple derivative. So your fx is this guy, fy is this one here. So if you calculate fxx, looking at the first one here, take another partial derivative for this term with respect to x. So that's 24 times 2 is 48x. This is 0. So 48x. And then for fyy, so taking partial derivative of this term with respect to y, so that's 6y. And fxy, now if you recall that, now I mentioned that in this class, we're going to all deal with a nice function. So nice function basically means fxy equal to fyx, right? Yeah. So you can go from either this one or this one, then you calculate fxy or yx, so it will be the same thing. So let's say fxy. So you take partial derivative of the first term with respect to y. This is gone. The second one leave us a 6. So fxy should be 6. Okay. So finally, you get all of these three terms in here. So then we can look at individual points. First point we want to look at is for this location 0, 0 location, right? So plugging 0, 0, which is a equal to 0, b equal to 0, plug it into the three terms at here. We have fx equal to, so fx 0, 0 equal to 0, and fyy 0, 0, okay, equal to 0 here. fxy, no change, is still 6. Okay. That's for this location. Okay. So now we're ready to test basically to test the point here. So let's plug into fyy minus fxy squared for this term, the Hessian, right? The Hessian term. So 0 times 0 minus what? Minus -6 squared, which is -36. Okay, so now go back to the theorem number 2. Theorem number 2 at here. Okay, so now can you tell me what type of point for that location. Which case? Which case is it? Number 3. So if number 3, then the 0, 0 location is a saddle point. Okay, so this is basically saying 0, 0 is a saddle point. So I'll show you what this graph look like, okay, once we finish this testing. For the other location, -1/2 and 1, -1. For this particular location, we do the same thing. We calculate fxx. So that's 48x. So 48 times that, so -24. And fyy. So 6 times y. 6 times y is -6. And fxy, no change, is still 6. Individually, each term is like that. So now all together, so let's take a look at together here. Basically, we calculate fxx, fyy minus fxy square. Okay, calculate this term. You plug in all the terms here, right? Plug in all the term. So you get 108. Now that's greater than 0. Okay, it's not less than 0 anymore. So this is previous one is less than 0. So this is greater than 0. So then you look at the theorem number 2. Okay, so fx fyy minus fxy greater than 0. So that's great. So there got to be one of the case 1 and case 2. Then you look at the sign for fx here. What's fx again? It's a -24. So it's less than 0. So then this location AB give us a local maximum. And then you can see fx here is basically less than 0. So then we get -1, -1/2, -1 is a local maximum. Okay, maximum. A natural question will follow from here is, okay, if this point is a local maximum, then what's the value of the local maximum? How do you calculate? How do you calculate the value of this local maximum? Yes. Absolutely, yeah. Right. So plug it into. So basically, value of local max equal to f. Plugging this value into the original function. Original function is given on the top. You calculate, you get 1. So your local maximum value is 1. Okay. For saddle point, you don't have to. Okay. Saddle point, you don't have to. So that's the typical process for finding mean or max for a surface. Okay, doesn't matter what type of surface it is. You just need to go through the first derivative test and second derivative test, and follow the instructions given by the theorem 1 and theorem 2, and then you should be able to nail the information. Okay, so I'll show you what this graph looks like here for this function here. So this graph here looks like this. So look like this. It's like a little bird here. So this one here, okay, is that local maximum, and this point here is the what? Is that saddle? Okay, yeah. So if you go from this point to one direction, it goes down. If you go another direction, it goes up. So that's why it's saddle here. Okay, yeah. If you're interested how it's plotted, and there's some command here how they're plotted here. Okay? Yeah. And if you keep going, there's no boundary set for this question. If you keep going to infinite x and y, so there's no other basically extreme points anymore, right? Yeah. Okay. So That's basically for function f of x, y, the mean and the max value at here. Okay. Any questions? Yes. fxy. Here, right? Yeah. Actually, I didn't calculate because you see here, this is your fx here, right? Or this is fy. If you take a partial derivative with respect to x based on y, or if you take a partial derivative with respect to y using fx, so this gives us fyx, this gives us fxy, right? Yeah. So if you calculate this partial derivative, look at the first one. What's this term? This is your fx here, right? What's the partial derivative this term with respect to the y? This is a constant considered. There's only 1/6, so that's 6, right? The second one here, you calculate this one with respect to x. Sorry, what's that? Yeah, with respect to x. This is 0. This is 6. This is 6. So fxy is 6 here. Okay. Yeah. Okay. So I'm not going to go into too much detail in the next lecture, but maybe just to raise the question here. So basically, the type of question what we're dealing so far at this for this one here, it's just you draw a surface, okay? Then the question asked is, can you find basically like those local mean and local max? Okay? That's the question we just solved here. Okay? Yeah. Now there's another type of question, right? Another type of question here is this. Okay? So it's the same surface, for example. Okay, it's the same surface, right? Same surface. Okay. For the first case study here, when you find the local mean, local max, then what happens is you have no constraint, right? You have no constraint over the xy value. You can vary the xy value anywhere within the plane. You can pick a point here, here, here. Then you can plug it into this surface and look for, okay, that's a mean, look, that's a max, right? So no constraint in terms of xy value. But often in time, right, then what happens is you have actually a constraint to the xy here. For example, you may say is, you cannot change your xy to anywhere else. Your xy has to be on this line at here. Is that okay? Right? So you cannot pick a point at here. You cannot pick a point at here. Your x and y are constrained to this trajectory, to this straight line, or to this straight line, or to a curve. Who knows? Okay? Yeah. Now that's a so-called a constraint problem now. If you have a constraint at here, and then the question here is, as you're walking along that constraint trajectory, what will be the local mean and the local max based on the trajectory traced out on the surface there? That make sense? Yeah. So if you go into the enemy line, you can't go anywhere else but that trajectory. But you wanted to know where the weak point is or the strongest point is. So that's basically so-called the constraint optimization problem here. Okay, so that we'll deal with our next lecture. Okay, yeah. I'll let you go over early because you have midterm. Yeah. Okay.